Hi everybody. This is section 7.3.1, Hypothesis Tests for a Population Proportion, Lesson 1. So before we begin, I want to begin with a scenario. Normally, if we were in class, I would pull out a deck of cards and run an experiment with everybody, or play a little game, but because we are not able to be in class, I'm instead going to give you a scenario. So, please write down the following scenario on a separate piece of paper. I'm going to read it to you. A man on the street pulls out a deck of cards. He says the deck is fair. That means it's half red and half black. Okay, it's a regular deck of cards. He proposes a game. Pick a random card. If it is black, you win, and if it is red, you lose. You play the game 8 times in a row and draw a red card every time, losing 8 times in a row. Okay, so that is the situation. So, is the deck of cards fair? So, let's go ahead and read into this a little bit, okay? So think about the results of the activity we just conducted as you answer the following questions. So before we played this game with this random person on the street, we had no reason to believe that the deck was not fair. Do you believe that the deck is fair now? Well, it's a little suspicious, right? We got 8 red cards in a row. So that seems like it could be a little too weird, right? So do I believe the deck is fair? You may say yes. Some people say yes, some people say no, but I would say no. It seems like the deck may not be fair. Okay. Notice I'm not saying it's not fair for sure. It just seems like what we witnessed was unlikely, right? So, you have seen only 8 cards, and yet you have made a decision about a collection of cards that is actually much bigger. What justifies such a decision? So, understand that we didn't see the whole deck. We only saw 8 cards, right? And so we're making a decision about the entire deck. So why are we allowed to do this? Well, we drew the cards randomly, didn't we? So since the cards were chosen randomly from the deck, the sample is most likely representative of the deck. How did probability factor into your decision-making process? Well, we agree that I didn't calculate an exact probability, so we don't know how weird it was to get 8 reds in a row, but it seems pretty weird, doesn't it? So let's just say that it is a very unlikely thing. You guys can probably agree that picking 8 red cards in a row out of a deck is probably pretty unlikely, right? So let's just say getting 8 cards in a row is very unlikely if the deck is fair. Therefore, I believe the deck is not fair. Okay? This is called using evidence, right? I saw evidence and now I'm thinking, wait a minute, I don't think the deck is fair, because if it were fair, what just happened is extremely unlikely. Okay? So next steps. You just made a decision about a population that you did not observe completely. Your decision was based on a small sample. In statistics, sample data helps us make decisions about populations through a process known as hypothesis testing. We have just conducted an informal hypothesis test. We began with an assumption about the deck. What was our assumption that we had, right? We'll talk about that in a second, but we began with an assumption about the deck. Then we gathered sample data. Upon examining the data, the likelihood of what we observed led us to make a conclusion about the entire deck of cards. Okay, let's read this language tip a little bit on the right. It says, a hypothesis is an assumption or claim. In statistics, we use sample data to test hypothesis about unknown population parameters. So think about it this way, right? Somebody makes a claim, and we are trying to test to see if the evidence supports that claim or not. Okay? If not, we reject the claim, and if it supports the claim, then, well, I'll get into more detail in a second, okay? So hypothesis tests include 4 steps. The 4 steps are: 1, determining hypothesis; 2, collecting data; 3, assessing the evidence; and 4, stating a conclusion. The following questions show how the steps fit with our reasoning during the card drawing activity. So step 1, determine the hypothesis. Every hypothesis test makes an assumption about the value of a population parameter. Remember, that's our P. That's the thing we don't know, right? That value is then challenged by the test. The parameter that we consider here is an unknown population proportion. The assumption that we make about its value is called the null hypothesis. We usually assume that a deck of cards is fair. What assumption are we making about the value of the population proportion of cards in the deck that are black? Okay, so what do we think P is? So P would be the proportion of black cards in the deck. So if we're assuming that the deck of cards is fair, then that means we're assuming that half of the cards are black, right? So then what would I put for my P equals here? My P would equal 0.5, right? That's the same as a half. So this is what we're assuming. This assumption is the null hypothesis for card drawing activity. So you saw 8 random cards in the deck. Did the sample data convince you that the proportion you assumed above might not be true? In other words, did those 8 cards provide evidence against this assumption that we made of P equaling 0.5? So I would say yes, right? We are definitely, or I'm at least definitely convinced by the sample of 8 cards that are all red. I'm convinced that there's no way that the cards are half black. So I'll say since none of the cards were black, it seems very likely that less than half of the cards were black. Okay. Part C. Do you feel that it is valid to use data from relatively small samples to make decisions about entire populations? Think about how convinced you were about the fairness of the deck. So do we think this is valid? I mean, how can we say that a deck is not half black if all we did is saw 8 cards? So we need to be comfortable with the fact that we are never 100% sure of anything in statistics. However, we base our results on what is most likely to be true. In other words, we are usually going to be right in statistics. Okay, so yes, we can use samples to make decisions as long as the probability that we are wrong is low. All right, we don't want to be wrong when we make a claim or when we say something. So what we do is we make sure that there's a very high chance that we're right. Or another way to say that is that there's a very low chance that we're wrong. Okay? Okay. Part D. Do you believe that the true proportion of black cards in the deck is less than, greater than, or simply different from the value given in question A, 2A above? So we think that there's probably less than half of the cards are black, right? We don't think that there's more black than half. So it's enough. I think the evidence is strong enough that we could say, I believe P is less than 0.5. Remember, P in this problem is the proportion of black cards in the deck. The belief you expressed in question 2D opposes the null hypothesis. Okay, do we understand what that means? It opposes it. This is contradictory, right? Our null hypothesis says that P is equal to 0.5. However, now we're saying that we think P is less than 0.5. So this is a contradiction to the null hypothesis, and so we call this the alternative hypothesis. Normally, we choose the alternative hypothesis before gathering data, okay? However, we're making an exception here just to teach the concept. We now use what we know about probability to show how strongly our evidence supports this alternative. If the evidence for the alternative hypothesis is strong, we will reject the null hypothesis, okay? In other words, what we want to make sure of is that the probability that we are wrong is really, really low. And if that's the case, then we're going to make our decision. So step 2, collect the data. Once we have identified the null and alternative hypothesis, we gather and summarize data, okay? All methods of inference in statistics assume that we are gathering data from simple random samples. So explain if and how your instructor ensured that data were gathered randomly from the population of cards. So I apologize if I didn't say this before, but we needed to state in the beginning of the problem that the cards were randomly selected from the deck. So let's just say the cards were randomly selected from the deck every time. Okay. Part B. What were the sample size and sample proportion of randomly selected cards that were black? Well, we took 8 cards, didn't we? So the sample size is 8. And what was p hat? Well, p hat is the proportion of cards that were black. And so since I said that we got all 8 red cards, right? They were all red. We got 0 out of 8. So if we do that in our calculator, we actually just get 0, because 0 divided by any number is 0. Okay, let's keep going here. Step 3, assess the evidence. We have summarized the sample data with a sample proportion, the proportion of black cards in the sample of 8 cards. Our job now is to determine if this sample evidence is strong enough to reject the null hypothesis in support of the alternative. We determine the strength of our evidence through probability. The probability, called a p-value, is computed assuming the null hypothesis is true. The p-value is the probability of observing a statistic that is at least as extreme as the one we gathered. Okay? If the criteria for approximate normality are satisfied, we can use the normal distribution to determine this. If not, we must use other methods. Okay, so what are we saying here? We have just introduced a new term called a p-value. The p-value is the strength of our evidence. It determines how strong our evidence is. Okay, look at this language tip on the right. It says the p-value is the probability of observing a statistic at least as extreme as the one we have if the null hypothesis is true. So we're trying to see how likely the scenario was. Okay, so let's move on. Part A. The criteria for approximate normality are not satisfied for this example because the sample size is too small. Okay, so this is going to be a complicated example, much more complicated than normal examples, because usually we're going to choose our sample size large enough so that we can find the p-value using the normal distribution and our calculator. Okay, but it's okay. This will still allow us to teach the method, okay? So what we're going to do is we're going to use the multiplication rule for independent events to compute the p-value. Assuming the null hypothesis is true, what is the probability that a randomly selected card is red? Okay. Well, the probability that we get a red card, if we assume that the deck is fair, the probability of getting a red is a half, right? This is the same as 0.5, but we can write it as a fraction as well. It's the same thing. So if the probability of getting a red is 0.5, now we're going to use the multiplication rule to determine the probability that among 8 cards, there will be no black cards. So in other words, what's the probability of getting a red 8 times in a row? Remember, we're assuming that we have a fair deck here. So we're trying to see, okay, if this guy on the street was telling the truth, what are the chances of getting 8 red cards in a row? So the probability of getting 8 red cards in a row, since we were putting the card back each time we played the game again, these are independent events, and so we just have to multiply 1/2 8 times. We do 1/2 times 1/2 times 1/2 times 1/2, and we do that 8 times in a row. Which, by the way, is the same as 1/2 to the 8th power. So if you do 1/2 to the 8th power on your calculator, you end up with the following probability. You end up with 1 over 256. But if we were to write that as a decimal, we would actually get 0.0039. 0.0039. Okay. It didn't tell us how much to round it, so I rounded it to 4 decimal places. However, if I wanted to round it even more, I could round it to 3, and it's 0.004. Now let's think about what this number means, okay? So we computed the p-value assuming, oh, by the way, what we just found is the p-value, right? This probability is the p-value. So I want to make sure we all understand that this guy, p-value, is that calculation. So we computed the p-value assuming the null hypothesis was true. Out of 52 cards, your instructor randomly selected 8, and none were black. The p-value tells us how likely picking no black cards in 8 draws would be if half the deck was black, right? So in other words, the chances of getting 8 red cards in a row, if the deck were a fair deck, is 0.004. Does the p-value make you question the null hypothesis? So think about it. Is this strong evidence against the deck being fair? The answer is yes. Okay, because this is a very low chance of that happening, right? If something is super low chance, in other words, almost impossible, then that leads us to say that what we witnessed must not actually be the way we thought. In other words, it makes us think the null hypothesis, in other words, the fact that this is a fair deck, it must not be true. So let's write that down. The p-value being really low, 0.004, means getting 8 red cards in a row is extremely unlikely given the deck is fair. Thus, it is highly unlikely that the deck is not fair. Okay? So let's move on here. Step 4, state a conclusion. Statisticians use a rule about how small a probability should be in order for us to consider an event unusual or statistically significant. So there's another buzzword about, or another definition that we should know called statistically significant. If a p-value is low enough, we consider it statistically significant. Now, this isn't a subjective thing, okay? We're not gonna, you might wonder, well, what if one statistician thinks that something is unlikely and another one doesn't? And it doesn't really work like that. We all agree on the same number, or we just say the number as we give the problem, okay? So we generally consider events that occur with a probability of around 5% or less to be unusual or significant. In such cases, we call the 5% rule the level of significance. Other levels of significance are sometimes used. So in this problem, if we assume the 5% rule, that means the level of significance is 5%, or sometimes we call this the significance level. So we assume that our deck was half black. Is it statistically significant if we observe a sample proportion of 0 cards that were black from a random sample of 8 cards? So the answer is yes, since so remember, we got a p-value of 0.004, and that is less than 5%, isn't it? So since our p-value is less than 5%, I'll say it this way. Since our p-value was less than 5%, the sample was statistically significant. When the p-value computed on the assumption of the null hypothesis is less than or equal to the level of significance, which is 0.05 in this example, we reject the null hypothesis and we support the alternative hypothesis. So let's make a decision now about the null and alternative hypothesis. Do we reject the null hypothesis and support the alternative, or do we fail to reject the null hypothesis? So because it is statistically significant, right, it means that the null hypothesis is extremely unlikely. So we reject the null hypothesis and therefore support the alternative hypothesis. Okay, so we reject the null and support the alternative. What does this mean? So part C says, explain what this means about the cards in the deck. So what does this mean? This means let me say, the evidence suggests that less than half the cards are black. Again, we're basing this on evidence. This isn't about personal feelings, right? So the evidence suggests that less than half the cards are black. Now, part D is making sure that we understand the difference between what we're doing and being certain of something. So, do you know the true proportion of cards in the deck that are black? The answer is no. Right? We don't know for sure that the population proportion is less than a half, right? So we believe less than half the cards are black. But we don't know what P is for sure. Right? In other words, we believe it's less than half, but we don't know for sure, and we don't know what it equals anyway, right? It could be, it could be that maybe a quarter of the cards are black, or maybe no cards are black. We don't know exactly. Or we could be wrong altogether, right? But we're just going off of the evidence. All we can say is that we suspect, because of the evidence, that less than half the cards are black. So we decided that the proportion of cards that are black is less than 0.5. This decision is about what the proportion is not, but be careful, we still do not know what the proportion is. Because of this, we never conclude a hypothesis test by saying what a population proportion is. Okay, we may state that we believe it is less than, greater than, or not equal to a value. Sometimes we will say that we can't disprove an assumed value, but this does not prove it. Okay, this is extremely important. I'm going to highlight this fact here. So, we never conclude a hypothesis by saying what a population proportion is. Okay. Again, this is saying that we can never prove that a certain proportion of the cards are black. All we can do is say that it seems like the claim that it's fair is false. So in other words, we're saying that less than half, but we can never say what the real answer is. Okay. All right. Let's move on. In 2011, studies showed that 41% of adults in the US claimed they worried about hunger and homelessness a great deal. Suppose that in March of 2017, a research group wanted to see if that proportion had increased. The group surveyed 516 randomly selected US adults and asked, how much do you personally worry about hunger and homelessness? 243 adults answered a great deal. So let's do the same thing we did before, except this is going to be a little bit different because we are dealing with a larger sample size here. So we're going to be able to use normality to help us with this problem. So what is the sample proportion of US adults who answered a great deal on the 2017 survey? Well, so P hat, it says that out of 516 adults, 243 said a great deal. So it's 243 out of 516. So if I do this in my calculator, 243 divided by 516, if I want to round it to 3 decimal places, I get 0.471. Based on the data gathered in the 2017 survey, do we know that the population of all adults who worry about hunger and homelessness a great deal is more than 41%? So think about what they're saying, okay? So the research group thinks that more people care about global warming, right? They knew that 41% did back in 2011. So they want to know, in 2017, do more people care? So they looked at a sample, and the sample showed that 47% of people care. So do we know for sure that overall the proportion has gone up? Well, this is evidence for that, but we're not sure how strong the evidence is, right? What if we just got unlucky and got a sample that had a few more yeses than normal, right? What if it hasn't really gone up? So the key word in this problem is this: do we know? So no, even though P hat is bigger than 0.41, we don't know if P is bigger than 0.41, right? So in other words, we know that the sample proportion is bigger, but we know that because of sampling variation, we don't know for sure if the real P is bigger than 0.41. But we're going to be able to use a hypothesis test to determine if this evidence is strong enough. So let's follow the hypothesis test process to investigate a possible increase from 2011 to 2017 in the proportion of U.S. adults who worry about hunger and homelessness a great deal. Step 1. Determine the hypothesis. Every hypothesis test has a null hypothesis and an alternative hypothesis. The null hypothesis is one which assumes the values are equivalent. In this case, the null hypothesis would state or assume that there has been no change between 2011 and 2017 in the proportion of adults who worry about hunger and homelessness a great deal. State the null hypothesis using this assumption. So what would P equal? Okay, so remember, the null hypothesis, you're always assuming the status quo. So think about it, right? In 2011, the status quo, the P was 41%, right? So this was P, right? This was P in 2011. So the new null hypothesis is that P is equal to 0.41. In other words, we're going to assume that the proportion of adults who worry a great deal about homelessness has not changed. Now, the alternative hypothesis is what the researchers hope to show is most likely to be true. They try to show that somehow things are different, right? We're trying to show that things have changed. The alternative hypothesis claims that the current population proportion is either less than a value, greater than a value, or different from the value. In this case, we believe that the proportion has increased from what it was previously. So what would our alternative hypothesis be? So if the null hypothesis is that P is equal to 0.41, it means that our problem is either going to have a greater than, or a less than, or just a not equal to. Now in this case, because we believe the proportion has increased, that means that the researchers think that maybe P is bigger than 0.41. Okay, so always, your alternative hypothesis is going to be one of those three symbols. And your null hypothesis is always going to be an equal. Okay, that's a good rule of thumb. And the way you know which one of those three that it is on the bottom is just read the problem, right? The original problem did say that the researchers think that there's a possible increase, right? Coming back up here, possible increase. They think it's gotten bigger. So that is why we would throw that into the alternative hypothesis. So step 2, collect the data. 8. Once we have identified the null and alternative hypothesis, we gather and summarize data. We also verified that the criteria for approximate normality are met. Part A. Statistical inference requires random sampling. Is there evidence that the sampling process was random? So let's go back up to the original problem. It says that it was randomly selected, okay? Right, see this part here? Randomly selected. I just put a little box around it. So because the experiment states that it was randomly selected, then there is evidence that it was random. So yes, the sample was randomly selected. Give the sample proportion of randomly selected adults who worry about hunger and homelessness a great deal. We already calculated this in question 6a. So when we look at question 6a, we notice that we got 0.471. So p hat is equal to 0.471. Next, part C. Is a normal model appropriate for this application? Remember to use the assumed population proportion to answer this question. Okay, so hopefully you guys remember the condition for things being normal or not. We need to make sure that the expected number of successes and failures was at least 10. Okay, now remember, we're assuming that p is equal to 0.41. We always assume the null is true. So this means that the expected number of successes is n times p, and the expected number of failures is equal to n times 1 minus p. So what is n here? What was the sample size? It says that they sampled 516 people. So this is going to be 516 times, times 0.41, or let me back up here, 0.41. So if I do that in my calculator, 516 times 0.41, I get 211.56. And if I do 516 times 1 minus 0.41, if I do that in my calculator, I get 304.44. And both of these are bigger than 10, aren't they? So this implies that normality criteria are met. A normal model is typically used to estimate the likelihood of observing a sample proportion at least as extreme as the value given above. Another way to estimate this likelihood is to run a simulation. Open the simulated p-value spreadsheet, and we're going to do this right now. So I'm going to cut to a screen share so you can see what I'm doing. So I've pulled up the spreadsheet that the problem asks for, and it says enter the population proportion from the null hypothesis, the sample size, and the observed sample proportion. So I'm going to enter all of that here. For p, I'm going to put 0.41. And for n, my sample size, I'm going to put 516. And then for left tail, it says that we should change it to right tail. So I'm going to select down. I'm going to select right tail here. And what was my p hat that we got? We got 0.471. So let's go ahead and change that here, 0.471. So this is what we got. Okay. So you can notice here, by the way, that almost everything is red. I mean, we would have to zoom in quite a bit just to see that there is no, we would have to zoom quite a bit to see where there isn't red, right? This is almost all red. And if you look right here, you'll notice that we actually have a tiny bit of non-red here. So out of these 1,000 dots, okay, out of all of those dots, it says that there are only 2 times where we got something that was at least 0.471. Okay, So how many of the simulated, so let's go ahead and fill this out. It says, how many of the simulated sample proportions were at least as high as the sample proportion we calculated? So it says 2 sample proportions were at least as high as 0.471. Okay, so that's what it says. What proportion of the simulated sample proportions is this? Okay, well, that's 2 out of 1,000, right? So this is 2 out of 1,000 samples, or around 0.0024. Okay, I'm hoping that we see that this is a very, very small value, right? Very small value. So let's look at part E here. It says, what does your answer to question 8D tell you about the sample proportion we calculated in question 8B? The sample proportion we observed, which is 0.471, is extremely unusual. Unusual. Oh, I see. I spelled it wrong. Unusual if we assume the null hypothesis is true. Right? It's extremely unusual because there was only a couple of dots to the right of that. So in other words, getting something that high is weird. Okay? So hopefully that demonstration was clear, and we're going to keep going here on step 3. Step 3, assess the evidence. We have summarized the sample data with a sample proportion to use as evidence to help determine whether the population proportion has indeed increased since 2011. We now determine the strength of our evidence with a p-value. Remember, the p-value is the probability of observing a statistic that is at least as extreme as the one that we gathered. The simulation generated 1,000 sample proportions based on the assumed population proportion and sample size. Because the criteria for approximate normality are satisfied, we can use a normal distribution based on standard error to determine the p-value. So just to touch base here, we did just use that simulation, but we don't need the simulation. Remember, when you have a normal distribution, you can find the exact answer by using your calculator. Okay, so that's what we're going to be doing. So to find the p-value, we use a normal distribution, and according to our null hypothesis, what is the mean of the sampling distribution? So we know that the mean is just going to be p, which is 0.41. So I'm going to put that in there. What is the standard error of the sampling distribution of all sample proportions? So remember, we already have this formula from previously, but now we're assuming that p is true. So we don't use p hat in this, we use the actual p. So if I put p in there, I get 0.41 times 1 minus 0.41. And then I divide that by, what was our sample size in the problem? I already forgot. Let's see, 516, right? And so I put 516 in there. So I have showed this with the calculator multiple times, so I'm going to skip showing it this time. So when I put this in my calculator, I do recommend that you try it out on your own to make sure that your answer matches mine. But when I put this in my calculator, I get the following. I get 0.022. So 0.022. So this is what I get for the standard error, okay? So what we're going to do is visualize what we're talking about here to see how unusual our answer was. We already know it was pretty unusual because we did the simulation, but we're going to go ahead and work through the picture, okay? So we want to scale it based on P and the standard error. So we know that this guy would be 0.41 here. And then if I add, so 0.41 plus 0.022, I get 0.432. And if I add 0.022 again, I get 0.54. And if I add 0.022 again, I get 0.476. And if I subtract 0.022 from this, I get 0.388. And if I subtract 0.022 from that, I get 0.366. And if I subtract 0.022 from that, I get 0.344. Okay, so this is what we get for the picture. So let's keep going. Remember, each of those is a standard deviation, right? So let's keep going. The p-value is the probability of randomly observing a sample proportion at least as extreme as the one gathered in our sample, assuming that the null hypothesis is true. So shade the area under the normal curve above that corresponds to this probability. So what was our p hat? So remember from before, p hat was 0.471. So where is 0.471? I would say that it's right about here. So it's this tiny little part that I shaded, right? This would be 0.471. Doesn't look very likely, does it? Okay. So we're going to keep going here. Let's actually figure out that shaded area. And we know how to do that, don't we? Using the normal distribution. So part E. To find the area shaded above, we need to compute the z-score of the sample proportion above. We can use the mean and standard error to compute the z-score of our p-hat value. So remember, we're just going to do the p-hat minus the p and then divide it by the standard deviation. So this is a formula we've seen before. So this would be 0. Oh, let me back up here. Let me choose black. So 0.471 minus 0.41 and then divided by 0.022. Okay. So I'm going to do that in my calculator. Don't forget to do the top part first. You can put it in parentheses. And then we do the division. So when I do that, I get the following. 2.77. 2.77. Remember, this is a z-score. Don't forget what the z-score represents. So if we come back up here, that makes sense, right? Because this is 1 standard deviation, this is 2 standard deviations, and then it's almost a full 3 standard deviations above, right? That's why we got 2.77, okay? So now we're going to do the p-value. The probability, it says use technology or tables to find the normal probability of observing a z-score at least this large. This is going to be the p-value. So remember, it's going to be the probability that z is greater than or equal to 2.77, right? That's our z-score. So how do we actually find this? Remember, this is going to be the normal CDF. And what's the lower limit? Well, because we are shading to the right, that means the left point is 2.77, and the upper limit is going to be infinity, or I can write 1e99. So this is what I'm going to put in my calculator. Let me demonstrate it on the calculator itself. Okay, so let's go over to the calculator. We know we want to do normal CDF, and the lower limit is 2.77. The upper limit is 1e99. So coming over to here, we're going to do second distribution. And for me, the second one down is normal CDF. So I hit enter. I'm going to put 2.77 on that one. And on this one, I'm going to clear it out, and I'm going to write 1 and then second EE99. I'm going to go down to paste, and I'm going to hit enter and then enter again. If I do that, I get 0.003 if I round it out. Okay, so from our answer, we got 0.003. So this is the p-value that we got using our calculator, and this is going to be a similar process for all of these problems, okay? We're going to turn it into a normal CDF problem. Now let's read part G. It says, the null hypothesis assumes that there is no change in the proportion of adults in the US, p equals 0.41, who worry about hunger and homelessness a great deal. But we observed a sample proportion, p hat equals 0.471, that was larger. Does the p-value indicate that the larger sample proportion we observed was likely or unlikely given a population proportion of 0.41? Well, we got a very small p-value, didn't we? 0.003. What does that mean? It means we observed something very unlikely. So let me write that down. The larger sample proportion we observed is very unlikely if we assume p equals 0.41, since the p-value is very small. And we're going to go into this more in the next step because we need to state our conclusion, okay? So we also need to think about the level of significance that we care about, okay? So let's look at the next part. It says step 4, state a conclusion. Number 10, now that we have computed a p-value, we can make a decision. We have stated that when a p-value is less than our 5% level of significance, the sample proportion is statistically significant. This leads us to believe that the null hypothesis is unlikely to be true and tends to support the alternative hypothesis. So is the observed sample proportion statistically significant? Well, our p-value was 0.003, and how does that compare to 5%? Is that less than 5% or bigger? So hopefully you know how to compare decimals. This is indeed smaller than 5%. In fact, it's smaller than even 1%, right? Because it says 0.003. Even if it were 0.03, it would still be small, but this one is really small, so it definitely works, right? So this means, yes, p hat equals 0.471 is statistically significant. Does this lead you to support the alternative hypothesis? Yes, we support the alternative hypothesis. Right? Because we reject the null hypothesis. Let me actually write that. Let me write that right here. So we reject the null hypothesis since it is very unlikely. Okay. Remember, in a conclusion, we can support or fail to support the alternative, so we can support or fail to support the alternative hypothesis, but we never conclude that the null hypothesis is true. So this is important, guys. You are not proving the null hypothesis is true. What you're seeing is if the evidence against it is strong enough for us to reject it. Okay? The only way you would be able to prove the null is to sample the entire population, which is ridiculous, right? That's why there's an exclamation point there. Okay, I want you to think about what this would mean. A good analogy for this hypothesis test is the way that our justice system works in America. When the government accuses you of a crime and you have a trial, what they're trying to see is if the evidence is strong enough to say that you're guilty. But if the evidence is not strong enough, they have not proven you innocent, but what they say is that you are not guilty, right? We've all heard not guilty before. They're very careful. They don't say innocent, they say not guilty. So what they're saying is that we assume you're innocent, and then we see if the evidence is strong enough to lead us to reject it. And if not, then that means we fail to reject it. But it does not mean that we have proven it innocent. So just like that, we never proved the null hypothesis is true. Okay, so let's move on. Describe what this means with regard to the proportion of the population of adults in the US who worry about hunger and homelessness a great deal in 2017. So remember, we showed the alternative hypothesis was true. So if we go back to the alternative, remember our alternative hypothesis, way over here, is that P was bigger than 0.41. So we just have to state that in words, right? In the context of the problem. We cannot just say that. So how would we say this as a final conclusion? So we would say, at a 5% significance level, we always say the significance level when we're talking about a hypothesis test. The evidence supports the claim that the proportion of adults in the US who worry a great deal about homelessness in 2017 was greater than 0.41. So all we're saying here is that the evidence suggests, or the evidence supports the claim that it's bigger, right? That P is bigger than 0.41. So this is the way we need you to write your answers. You need to write a full English sentence that takes all of this into account. All right, everybody. Thank you very much for watching this video. The code word for this lesson is red. Thank you very much for watching. I hope it was helpful.